In 1935, Einstein rolled his eyes at quantum entanglement and dismissed it as nothing more than spooky action at a distance. Fast forward to 2025, and that same spooky effect now sits at the core of experiments in unhackable communication and trials for a future quantum internet. How did something Einstein mocked turn into the foundation of technology shaping tomorrow? And what does it mean for us that particles can stay mysteriously linked across space, no matter the distance? What Einstein once called spooky now protects bank transfers. Here's how. To see why, we need to start with Einstein himself. Einstein versus entanglement, from mockery to legacy. Einstein's uneasy relationship with entanglement began in 1935, when Boris Podolsky and Nada Rosen published what became known as the EPR paradox. In their thought experiment, they argued that quantum mechanics was leaving something out. If the theory were truly complete, it should not allow two particles to remain linked across vast distances in a way that appeared instantaneous. For Einstein, this violated the principle of locality, his conviction that no influence could travel faster than light. He ridiculed the idea with a phrase that would stick: spooky action at a distance. To him, this was not an elegant feature of nature, but a sign that quantum theory was unfinished, a placeholder until hidden rules were discovered. The contrast with his earlier work is revealing. Einstein had already shown the world that time and space were not fixed but flexible, bending under the weight of matter and energy. That was a radical leap, yet to Einstein it maintained coherence. A vast cosmic clock still ticked by rules, just different ones than Newton imagined. Quantum entanglement, however, looked like disorder. It suggested that two particles split apart to opposite ends of the universe. He imagined them as if tied by invisible wires, an unacceptable violation of the logic he had spent his life defending. To him, randomness and non-local influences belonged in mysticism, not physics. Yet his rejection did not stop others from taking entanglement seriously. Erwin Schrödinger, responding to the EPR paper, coined the term entanglement itself. He went further, calling it the defining trait of quantum mechanics, the thing that most clearly separated it from classical ideas. This disagreement set a stage that stretched across decades, Einstein calling entanglement a flaw, Schrödinger declaring it a foundation, and physicists everywhere wondering which of them time would prove correct. The real turning point arrived in the 1960s, when John Bell reframed the debate. Instead of arguing in abstracts, he turned entanglement into a measurable prediction. Bell showed that if particles were only governed by hidden variables, a classical explanation in line with Einstein's realism and locality, then correlations between their outcomes would obey certain restricted patterns, now called Bell's inequalities. But if quantum mechanics were right, the results would break those limits. This was a revolutionary shift. The question could finally be answered not by opinion, but by experiment. One clear example? Prepare two entangled photons, send them to separate detectors, measure their polarizations, and later compare notes. If their correlation went beyond Bell's inequality, quantum mechanics would win. That experiment was first attempted in 1972 by John Clauser and Stuart Friedman using entangled photons. Their setup, though limited by technology, already showed results aligned with quantum predictions. Over the next decade, refinements accumulated. In the early 1980s, Alain Aspect and his team in France ran a series of sophisticated experiments designed to rule out loopholes. Fast-switching polarizers ensured that a decision made on one side of the experiment could not influence the other before the result was registered. Once again, the inequalities fell precisely as quantum mechanics had predicted. It became harder to imagine that classical hidden variables could explain away the correlations. Still, physicists wanted more certainty. Each experimental round raised new questions. Could detectors be missing too many particles? Could subtle communication between systems still play a role? Through the 1990s and 2000s, Anton Zeilinger and others pushed entanglement into new territories. They sent photons through kilometers of optical fibers, bounced signals between telescopes, and even demonstrated entanglement across distances measured in hundreds of kilometers. These bold feats not only tested Bell's framework in increasingly extreme conditions, they also hinted at the practical applications we see being explored today. Then came 2015, when multiple groups in the Netherlands, Austria, and the United States carried out what were called Loophole-Free Bell tests. By combining highly efficient detectors with fast, Space-like separated choices of measurement settings, they closed both the detection loophole and the locality loophole at once. The results were decisive. Bell's inequalities were violated, quantum mechanics was upheld, and Einstein's vision of a hidden local explanation was set aside. Later recognition came in 2022, when the Nobel Prize in Physics went to Aspect, John Clauser, and Anton Zeilinger for proving through decades of experiments that entanglement is real and measurable. The implications of these results reach far beyond resolving a philosophical standoff. When Bell's inequalities were broken in lab after lab, it demonstrated that reality at its most fundamental cannot be accounted for by a collection of independently existing parts obeying straightforward local rules. Instead, particles are bound together by correlations that defy separation. Entanglement means that what happens to one system cannot be fully described without acknowledging another, regardless of distance. Experiments gave flesh to what had once been only mathematics, forcing physics to embrace a connectedness built into nature itself. And where does that leave Einstein? It would be oversimplified to say he was simply wrong. His instinct that entanglement threatened our understanding of reality was absolutely correct, just not in the way he expected. He warned that allowing for these spooky bonds would destabilize the neatness of physics. Experiments later showed that destabilization was unavoidable because it reflected how the universe actually functions. His caution was rooted in consistency, and it is precisely that consistency which his view could not maintain once tested. Rather than undermining his legacy, the story highlights his role as both critic and catalyst. His skepticism forced others to sharpen their theories and build the experiments that proved entanglement true. The irony is difficult to ignore. What Einstein once dismissed has become a validated cornerstone of modern physics. The particle connections he regarded as implausible now support technologies that will transform how information can be processed and shared. They serve not as a quirk, but as a resource, guiding researchers in building communication systems designed for security and performance beyond anything classical physics could allow. The skepticism of one era has become the toolkit of another. This perspective also matters because the story does not stay confined to textbooks or laboratories anymore. From satellites sharing entangled photon pairs over vast distances to quantum keys that secure digital communication, entanglement has begun moving into the structures of daily technology. As experiments keep proving its reliability, engineers are finding ways to turn this strange physical principle into a functional tool. What once seemed to Einstein like disorder is now order of a new kind, one that can be applied to the networks and data systems shaping the future. The journey from Einstein's challenge to modern experiments underscores a remarkable lesson. Nature is often stranger and more interconnected than common sense would suggest. But instead of ending as a curiosity, these experiments have built the foundations of an entirely new technological era. And that transition brings us to a pressing question. If entanglement is no longer just a puzzle for physicists, what promises or risks might unfold as it begins forming the backbone of systems built for the world we live in today? The quantum internet of 2025. What scientists are working toward in 2025 is nothing less than an entirely new type of internet, one that is governed not by clever code or faster processors, but by the rules of quantum mechanics. The current internet connects machines with extraordinary efficiency, yet every transaction and every message still carries a basic vulnerability. Encryption can be broken, servers can be compromised, and digital trust can vanish overnight. A quantum internet aims to address that fragility, not with stronger passwords or layers of software, but with the very physics that underlies nature itself. The first question engineers asked was simple. Could a network itself make intruders visible? In classical communication systems, information can be copied or intercepted without the sender or receiver ever noticing. Quantum systems behave differently. When entangled particles form the channel, any attempt to probe them leaves an unmistakable disturbance. The security, in this case, does not rely on probability or on secrecy of algorithms. It is guaranteed by the physical laws governing the particles. The connection itself becomes a sensor, a tripwire invisible yet inescapable. Consider how such a connection works. A lab prepares pairs of photons whose properties are entangled, meaning the measurement of one instantly reveals information about the other. One photon is kept, the other travels through optical fiber or potentially a satellite link to a distant node. Even when separated by hundreds or thousands of kilometers, the bond persists. If anyone touches the channel, measuring, altering, or trying to copy, the entanglement shifts, signaling intrusion instantly. The communication does not transmit faster than light, but its integrity is absolute because any interference leaves evidence that cannot be erased. Several regions have pursued this approach in different ways. China has built an early lead with satellite experiments, most famously through the Qubits satellite launched in 2016. Qubits demonstrated quantum key distribution across 1,200 kilometers and even managed intercontinental secure exchanges between China and Austria, proving quantum secure signals could be sent well beyond the reach of a single nation's ground network. Europe, through its EuroQCI initiative, is pursuing widespread integration of quantum secure infrastructure that links research centers, government facilities, and eventually civil networks across the continent. The United States has focused on advanced fiber-based testbeds and integrated photonic systems through collaborations between national laboratories, technology companies, and defense agencies. Each region emphasizes a different path: satellite distribution, optical networks, or photonic chips, but all aim at the same landmark: reliable quantum communication infrastructure. Recent demonstrations have underscored just how far this development has come. In one milestone, researchers achieved photonic quantum teleportation between chips over 12.3 kilometers of fiber, showing that entanglement-based transfer of quantum states can work over distances well beyond a laboratory table. In another, space-to-ground quantum key distribution proven by satellites like Qubits revealed that links can cross thousands of kilometers and still maintain high fidelity. These achievements have shifted entanglement from theoretical novelty into a tested resource that can be scaled into real networks. While no single experiment accounts for a complete intercontinental quantum internet, together they show the necessary building blocks: entanglement that survives vast separations, photon transmission through atmosphere and fiber, and repeaters that extend fragile signals further than optical limits alone would allow. The consequences for existing encryption are stark. Classical digital security relies on mathematical puzzles, keys generated through algorithms that with today's hardware would require impractically long times to crack. But this line of defense erodes when quantum computers mature enough to run algorithms capable of breaking standard cryptography. In other words, the very machines built on quantum principles will one day shatter most of the codes guarding financial systems, emails, and medical records. The only way to secure information against that future is to turn those same quantum principles into protection mechanisms. Entanglement, used correctly, can do what no software patch can: enforce secrecy by physics. This shift explains why projects are no longer treated purely as academic curiosities. Entire economies depend on constant secure communication, and leaks cause more than financial losses. They damage public trust and have political consequences. That is why China, Europe, and the United States have invested heavily in parallel efforts. Each wants to shape the architecture of the first quantum internet and avoid dependence on someone else's infrastructure. The incentives are enormous, but the distinction lies not in claiming dominance, but in how each chooses to reach the same goal: satellite constellations, continent-spanning fiber networks, or chip-scale devices woven into existing grids. Building such a network has also forced scientists to overcome technical challenges that yield new spin-offs. Photons must retain coherence while traveling through noisy environments. Detectors must register single particles with extraordinary efficiency, and timing systems must synchronize at levels far beyond conventional internet standards. Solving these problems has created tools that reach beyond security. Quantum links allow distributed sensors with unprecedented precision, clock networks that can measure time with sub-nanosecond accuracy, and even possibilities for astronomical observatories around the globe to combine signals as if acting as one giant telescope. All of these are side effects of solving how to send secure messages through entanglement. What sets the quantum internet apart from all previous forms of communication is its defensive posture. Classical systems can always be broken if an attacker is clever enough. Firewalls, antivirus software, and cryptographic updates are responses in an endless game of defense catching up to offense. A quantum internet changes the premise. Hackers cannot remain invisible. The attempt itself shows up in the altered statistics of measurement results. The very act of trying to copy information warns the participants. That makes the balance of power, so often tilted toward attackers, suddenly shift toward those who wish to safeguard communication. For the first generation growing up with such networks, the perspective may look very different. Security might not feel like a privilege or an optional feature. It could appear instead as a natural standard. Stories about stolen credit card numbers or intercepted private conversations could one day sound like relics of a reckless era when systems left vulnerabilities wide open. In the logic of a quantum internet, privacy is not granted by institutions promising protection. It is inherent in how the connections themselves operate. The full global rollout will still take years, and challenges remain in cost, integration, and scaling. But the principle is already working in experimental networks, satellites, and specialized nodes. The concept that Einstein once doubted has not only survived, it is being engineered into the foundation of information exchange. Physics now guarantees what humans alone have struggled to enforce: secrecy that cannot be faked or bypassed. And that reliability is exactly what lets entanglement protect secrets. Next, how that actually works. Unhackable communication, science fiction turned real. Could communication really exist in a form where any attempt to intercept it is instantly visible? For decades, the answer was no. Encryption was the standard method, and while it provided strong protection, it was never permanent. Over time, computing advances eroded its strength. Every code, no matter how sophisticated, was in principle breakable. That left a lingering problem. As long as secrecy depended purely on mathematics, patient effort or technological leaps would eventually expose it. What was needed was not just harder encryption, but communication that built in detection of eavesdropping from the ground up. That is the central promise of quantum key distribution, often shortened to QKD. It does not rely on puzzles that can be solved. Instead, its protection comes directly from the physics of quantum mechanics. At first glance, QKD looks similar to ordinary encryption. Two parties exchange a shared key they later use to encrypt their messages. What changes everything is how that key is created. Rather than sending digital bits that can be intercepted without leaving a trace, the key is generated with entangled photons. Each photon has measurable properties such as polarization. When a pair of photons is entangled, measuring one instantly tells you about the other. Two parties, often called Alice and Bob, receive streams of these particles and measure them using randomly chosen orientations. Their results line up in a way that classical physics cannot explain. The trick is that if an outsider, traditionally called Eve, tries to enter the process, the delicate correlations fall apart. The eavesdropping reveals itself automatically in the chain statistics. Think of it like a rope stretched taut between 2 points. The moment anyone touches it, the rope snaps and both ends feel the break. To make that practical, imagine two banks trying to set up a secure channel. Each receives entangled photons through a dedicated link. They perform random measurements and then over a classical channel compare parts of their data, but not the full outcomes. If the shared statistics remain within the expected patterns, they can confirm no intrusion occurred and extract a secret key. If an eavesdropper tampered with even a fraction of the photons, the disturbance signals intrusion and the session is discarded. The key is either intact and safe, or it does not exist. There is no hidden middle state. Unlike conventional information, photons cannot be cloned without being changed. A law in quantum physics called the no-cloning theorem makes copying impossible. This is not just theory confined to chalkboards. QKD has moved well beyond laboratory demonstrations. Pilots are operating in real-world settings, though it is far from universal. In 2025, there are working deployments in specialized sectors, international banks, certain government channels, and high-security testbeds connecting research centers. In metropolitan areas, such as Beijing, Vienna, and Geneva, installed fiber loops already carry live QKD traffic alongside conventional data streams. In Canada and Europe, projects like QEYSAT and EuroQCI have tested satellite-based distribution of keys that cross entire regions. China's Mishias satellite extended this further by sending entangled photons across 1,200 kilometers, even proving intercontinental key exchange with ground stations in both China and Austria. Each of these demonstrations shows not only that QKD works, but that it integrates with real infrastructure. Adoption is driven by fields where any breach carries enormous costs. Banks need to secure transactions that flow every second across time zones. Defense networks demand higher confidence than mathematical codes alone can bring. National election authorities face pressure to protect communication against foreign interference, and healthcare systems holding some of the most sensitive data about individuals are testing QKD links to prevent leaks. For all of them, QKD is not yet a replacement for classical encryption, but a complement deployed in limited architectures where guaranteed detection of intrusion is essential. The security effect seems subtle, but its consequences are profound. In a system built on quantum keys, information cannot be silently copied and stored for later decoding. Any attempt to listen in creates noise that flags itself instantly. Security shifts from being a moving target, always under threat of future breakthroughs, to something rooted in the physical laws themselves. For the user, it feels ordinary. Employees log into their systems. They exchange files. Satellites beam photons through the atmosphere. The only difference is that their secret keys now come from particles that behave according to rules Einstein once mocked. That irony is striking. Einstein famously dismissed entanglement as spooky action, thinking it was too strange to build into a complete theory. Yet today, governments and corporations rely on that same spookiness to secure financial records, diplomatic messages, and health databases. What he once regarded as a flaw is now a standard defense mechanism against modern hacking. The idea dismissed as implausible is the very mechanism making tampering practically impossible to hide. It is also important to clarify what QKD is not. It does not let information travel faster than light. The actual messages still move through ordinary cables and satellites. What QKD distributes are unbreakable keys that later secure those messages. Once verified, the keys are combined with conventional encryption protocols. The difference is not speed but certainty. The keys cannot be intercepted without evidence. In effect, QKD creates a lock that fractures if anyone besides the rightful users touches it, a lock backed not by computational difficulty, but by physics itself. This shift reshapes how cybersecurity is designed. Whole industries have been built around detecting hacks after they happen and patching vulnerabilities. QKD reverses that posture. With every key exchange, intrusion shows up immediately as errors in the shared data. Hackers cannot remain hidden for weeks, quietly siphoning information. Every attempt to interfere leaves unmistakable evidence. That changes how banks plan their networks, how governments share classified information between continents, and how scientific collaborations move sensitive experimental data. Each leap forward in communication remade how societies connected. The telegraph carried words faster than ships. The telephone brought voices into everyday life. The internet enabled instant global links. In this new stage, the defining feature is not speed or convenience, but verifiable security. Across cities, quantum channels now join fiber loops. Satellites distribute entangled photons across national borders. Test beds demonstrate what full-scale connections might look like. The concept sounds futuristic, but for those using the pilot systems, it is already mundane. They send files, make calls, and carry out transactions without realizing fragile chains of photons are securing those acts. Picture the moment clearly while hackers continue to probe ordinary servers and prey on weak passwords. The highest value communications sit behind channels where intrusion cannot remain hidden. Financial transfers, medical records, diplomatic cables all move with a safety guaranteed by the quantum state of light itself. Instead of secrecy being a temporary protection eroded over time, secrecy becomes the baseline. Every attempt to tamper leaves behind a record. The system works not by creating perfect invisibility, but by ensuring visible warnings. Spying is no longer a gamble, it is immediately obvious. This is the curious fate of entanglement. Once dismissed, it has become the silent custodian of data flows that underpin the global economy. Invisible keys appear and vanish at the rate of 1 billion photons per second, guarding identities and secrets. The defense is not built by clever codes or hidden tricks, but by the laws that bind the microscopic world. And as we have seen, the same strange link that secures information also powers another frontier, machines that use entanglement not just to protect data, but to compute in ways no classical system ever could. Quantum computers and entanglement's secret power. When researchers turn their attention from secure communication to raw computation, entanglement reveals another dimension of its utility. Quantum computers embody this shift, and their distinguishing feature is not speed alone, but the way entanglement binds qubits into unified systems. Unlike classical machines that step through instructions line by line, Quantum processors derive their power through correlations that spread across particles, allowing calculations to emerge from patterns impossible to separate into independent parts. A useful comparison is between bits and qubits. Classical bits sit firmly as 0 or 1, switching rapidly but still limited to one state at a time. Qubits, however, can hold a combination of those states. Entanglement couples them so that the measurement of one fixes the outcome of another, even across large separations. This coordination makes a group of qubits behave like a single, inseparable fabric. To illustrate, some describe this as parallel realities, but a more grounded explanation is that qubits exist across multiple probabilistic states until a measurement collapses them into one. They do not run every possible computation fully formed, but they exploit interference among potential outcomes so only consistent solutions survive. This quality changes the landscape of what problems can be tackled. In chemistry, for instance, simulating how even a modest-sized molecule behaves overwhelms classical computers because interactions balloon exponentially. Entanglement offers a way to represent all those interactions together rather than one at a time. A complex energy surface can emerge within the relationships of qubits, and solutions that evade ordinary models become within reach. The difference is not about surviving longer calculations, but about redefining the problem space entirely. That representational leap has already been tested in practice. Early this year, quantum processed with a few hundred stable qubits produced folding predictions for proteins whose structures had long eluded conventional methods. These were not hypothetical molecules, but enzymes tied to neurodegenerative disorders where shape dictates function. Afterwards, laboratory verification confirmed the predicted structures matched reality. Where traditional machines had provided uncertain guesses, the quantum device achieved answers researchers could confirm in experiments. It marked a transition point, no longer waiting for quantum computing to catch up, but beginning to see results in active biomedical research. Other challenges follow a similar pattern. Logistics firms are trialing quantum processors to optimize multi-step delivery networks, where reducing fuel or travel distance translates to billions in annual savings. Material scientists are modeling catalysts and superconductors, expecting insights into designs that could lower energy losses or speed up reactions crucial to industry. Each of these tasks shares the trait of near unmanageable complexity. With entanglement, what once seemed irreducible becomes structured into solvable landscapes. Hardware progress now plays a decisive role. Cisco's Quantum Lab, for example, recently introduced an entanglement source chip operating at room temperature, generating hundreds of millions of entangled photon pairs each second while sipping less than a milliwatt of power. Crucially, over 99% of those photons are actually usable for quantum information. This kind of platform shifts development away from fridge-sized cryogenic contraptions and toward deployable systems suitable for data centers. The same expertise used in networking classical machines is being applied to link quantum processors, turning standalone devices into distributed architectures. Instead of searching for a single perfect machine, engineers explore how smaller connected processors may achieve practical use faster. Still, optimism must be balanced with constraints. Qubits are fragile, and entanglement collapses when disturbed by environmental noise. Keeping them coherent for extended periods is one of the greatest obstacles engineers face. Error correction remains a major research field, building logical qubits from multiple physical ones so that mistakes can be detected and compensated in real time. Progress has been steady, but each usable qubit today represents intricate engineering in cooling, shielding, and control. This is why quantum processors excel in specialized domains rather than replacing laptops or cloud servers outright. The daily applications of spreadsheets and websites remain safe in the hands of classical processors. Entanglement is too delicate to be deployed casually across every sector just yet. Concrete demonstrations matter in convincing people that these machines are more than hype. The unfolding story looks less like a sudden arrival and more like a series of thresholds crossed. What began with small laboratory prototypes has now reached trials outside controlled settings, handling biology, logistics, and material science in meaningful ways. Where once quantum supremacy sounded like a slogan, the present reality is narrower but clear. In well-chosen problems, entanglement delivers results classical methods could not reach. It provides not a universal speed-up, but targeted breakthroughs in fields defined by heavy complexity. Skeptics still raise fair questions. Will machines scale smoothly to thousands or millions of qubits? Can error correction ever be made efficient enough without consuming vast resources? These are open challenges, and there is no guarantee every hoped-for application will succeed. Yet dismissing quantum computing outright seems increasingly untenable when verified demonstrations show practical answers where there were none before. The lesson is that entanglement is not a magician pulling solutions from the air, but a physical principle engineers can harness with gradual, deliberate progress. The implications extend beyond science alone. Startups like Nirvanic are already exploring quantum computing as a foundation for AI systems, arguing that entangled states allow artificial intelligence to evaluate uncertain or unfamiliar inputs more flexibly. They aim to mimic how the human brain might process overlapping possibilities, drawing on conjectures that consciousness itself uses quantum effects. Though speculative, these projects hint at an expanding field where entanglement becomes not merely a solution to equations, but a platform for building adaptive machines capable of reasoning in dynamic environments. Taken together, these threads show a deeper theme. Entanglement is turning from a puzzle of theory into the central mechanism behind machines that rethink where computation's limits lie. Its secret lies not in speed, as newspaper headlines often imply, but in coordination among qubits that no classical logic can reproduce. When patterns emerge from interference and superposition, answers appear in forms no step-by-step pathway could provide. That is why a few hundred properly entangled qubits can rival millions of conventional processors working tirelessly, and why fields once closed off are beginning to see solutions. The path forward will keep combining breakthroughs in materials, chip design, error correction, and clever architecture. But the trajectory already shows a simple truth. The spooky connections Einstein distrusted are now opening doors far beyond encryption. They're powering calculations, simulations, and optimizations once declared untouchable. And the more these systems advance, the more entanglement becomes a tangible tool in the engine of science and society. Yet entanglement has one more role still to play. Its most counterintuitive trick is not in securing secrets or solving equations, but in making information itself move in ways that challenge everyday expectations about space and distance. That is where the story next turns. Teleportation isn't Star Trek, but close enough. Teleportation in quantum physics looks nothing like the science fiction scenes of glowing beams and vanishing bodies. What actually transfers is not matter, but the fragile condition of a quantum state. Instead of moving atoms from one place to another, teleportation allows the precise configuration of a particle, its quantum identity, to disappear in one location and reappear elsewhere. That distinction means no physical object travels, yet the information that defines the object state is successfully recreated at a distance. Far from remaining a curious thought experiment, this process has now become an essential working tool in research labs and test networks. It helps to clear this up at the outset. The public picture of teleportation remains based on popular culture, the instant relocation of objects. Quantum teleportation operates differently. It works by transferring knowledge of a system's state without sending the particle itself. Imagine a die resting on a table. In ordinary life, you could record the number on top and copy it elsewhere with no consequence. With a quantum particle, that kind of duplication is forbidden. The act of measuring changes the system. The only way to reproduce its state somewhere else is through entanglement. Two particles linked in that way allow a state to be exchanged over distance, though nothing physical makes the journey in between. The canonical teleportation experiment relies on three particles. Two are entangled ahead of time, one of them placed with the sender and the other with the receiver. The third carries the unknown quantum state to be transferred. The sender performs a special joint measurement between the third particle and their local half of the entangled pair. This action erases the original state, but encodes information into the faraway partner. With the help of a few classical bits sent afterward, limited by the speed of light, the receiver can reconstruct the original state exactly. No shortcuts occur, and the original is gone, ensuring perfect recreation without duplication. These experiments began modestly within a few meters in controlled laboratory environments. Over the years, distances grew longer, extending through spools of optical fiber across city-scale networks and then to orbiting satellites. One experiment linked ground stations with satellites hundreds of kilometers overhead, showing that fragile entangled states could endure atmospheric turbulence and long transmission paths. Each advance demonstrated that teleportation was not confined to chalkboard diagrams, but survived the practical challenges of real environments. By 2024, researchers reached another milestone that hinted at practical integration. At Northwestern University, teams teleported quantum information across 18 miles of commercial fiber carrying everyday traffic. This meant teleportation could operate on the same strands of optical cable that already support classical communications, a key step toward blending quantum and conventional infrastructure. In 2025, another important experiment pushed the concept even further into practical design, a demonstration of chip-to-chip photonic teleportation across 12.3 kilometers of fiber. Two independent silicon photonic processors exchange quantum states, not within a lab bench but as network devices, showing in principle how future nodes of a quantum internet might pass data seamlessly. Teleportation also underpins efforts to solve the distance problem for quantum communication. Photons carrying fragile states decay rapidly when sent through fiber or free space. Classical signals can be amplified to regain their strength, but quantum signals cannot be copied or boosted without loss. This is where quantum repeaters come in, and teleportation is their central tool. By linking entangled segments together through a process called entanglement swapping, repeaters extend secure links step by step. Teleportation moves the quantum state to fresh particles across each segment. Quantum memory, another development, allows entangled particles to wait in storage until every segment is ready, ensuring a long-distance path can be stitched together without collapse. Without teleportation, none of this would be possible. The misconceptions surrounding faster-than-light communication often surface here, so it is worth restating plainly. Teleportation does not allow messages to beat light speed. A classical communication channel is still required to complete the process, and that channel remains bounded by relativity. What teleportation guarantees is fidelity, not speed. It ensures the state is recreated without having crossed the space in any physical sense, but it operates squarely within the known limits of physics. By 2025, teleportation remains the subject of research testbeds rather than a hidden feature of consumer networks. Selected laboratories and prototype systems rely on it to pass quantum information securely, and satellite ground tests continue to demonstrate resilience across long distances. But it should not be imagined that ordinary email or video calls already ride on teleportation channels. These are evaluations of feasibility, laying groundwork for larger, more stable architectures. As those architectures grow, teleportation will become the workhorse carrying fragile states safely across networks that could one day reach continents in orbit. The elegance of teleportation comes from the challenge it overcomes, because quantum states cannot be cloned. Distributing them directly is impossible without risk of loss or tampering. Yet by accepting this limitation and working with entanglement, teleportation turns the obstacle into an advantage. Each destroyed state is reborn elsewhere with complete accuracy, immune to interception in the middle. Hackers cannot copy what physics itself prevents from being copied. The method is both secure and fundamental. These demonstrations have also spilled into quantum computing architecture. Researchers at Oxford University, for example, linked two independent quantum processors using photonic interfaces. Essentially, they teleported states between devices to make them behave like a single, larger quantum computer. Instead of building one massive machine that risks instability, smaller machines can be connected into functional clusters. This approach shows how teleportation is not only a communication protocol, but a strategy to scale computational power. The more these experiments expand, the more they reshape what teleportation means in everyday terms. It is not a trick for moving objects, but a technique for moving quantum information intact. Protocols that use it may one day support financial transactions, international security agreements, or scientific collaborations, ensuring that sensitive data cannot be intercepted unseen. Though no glowing chambers or swirling particles appear, the quiet transfer of states across fiber and satellites achieves something science fiction rarely imagined, a form of teleportation that is real, repeatable, and deeply practical. One can imagine Einstein's reaction if confronted with today's experiments. He would need reassurance. No person has vanished and no object has been disassembled. Yet the very principle he once found unconvincing allows physicists to shift information between distant nodes without any physical transport. The irony is gentle but striking. Spooky action has matured into a clean, measurable process that secures communication and expands computing all at once. Teleportation does not thrill visually. It plays out in detectors, photons, and streams of data crossing invisible fiber channels. Its achievement is measured less in spectacle and more in reliability. With each successful protocol, the boundary of what networks can achieve stretches further, proving that communication lines can carry states without ever carrying the particles. This is not a futuristic promise. It is a developing reality tested today in laboratories and prototype links that are paving the way toward tomorrow's infrastructure. And this is where a final point comes into focus. The same technique ensures that fragile entangled keys survive across repeaters, forming the spine of secure quantum networks. That detail links teleportation directly back to the central promise. Quantum channels too delicate to transmit normally become resilient when states are transferred instead of physically sent. That is how tomorrow's information ties itself not to codes but to physics. This is the trick that keeps quantum keys safe across repeaters. Coming up next, nature's hidden quantum tricks. What if the strange connections we struggle to engineer in laboratories were already built into the living world? Evidence suggests that entanglement and quantum coherence are not inventions of physics, but natural tools woven into life itself. Far from exotic curiosities, these effects appear in creatures as ordinary as robins and in processes as familiar as photosynthesis. Our most advanced machines still fight to preserve entanglement for milliseconds, while birds and leaves make use of it under the open sky. Robins navigate with quantum rules, while our labs still try to hold entanglement in vacuum chambers. Nature achieves it in feathers and chlorophyll. Among the clearest examples is bird migration. Small species such as a European robin travel from northern Europe to southern Spain with staggering accuracy, returning to the same regions year after year. For decades, scientists could not explain how such small animals crossed thousands of kilometers without getting lost. Sight and smell helped them locally, but could not account for precision across entire continents. Real progress came in controlled experiments when biologist Henrik Moritzen showed that disrupting a robin's vision also disrupted its compass. When one eye was covered, the bird lost its magnetic orientation. With the eye uncovered, its sense of direction was restored. No organ buried in the skull acted as a compass. Instead, the mechanism resided directly in the bird's eyes. The physics behind this navigation points toward entanglement. When light enters the robin's retina, it sets off a chemical reaction that creates radical pairs. Two electrons released in a correlated state. These electrons remain entangled, their linked spins responding to the direction of Earth's magnetic field. Shifts in these probabilities feed into the bird's neural processing, effectively giving it a magnetic compass. This is not speculation. It has been backed up by both behavioral studies and theoretical models of radical pair reactions. What seems almost unbelievable is that entangled pairs survive long enough in the noisy chaos of a living eye to provide stable information. With no knowledge of physics, the robin relies on entanglement to guide its path across continents. The resilience of this effect is particularly striking. In laboratories, entanglement usually demands lasers, isolation chambers, or ultra-cold environments. By contrast, the robin carries out its long migrations in warm, wet tissue teeming with molecular noise. Yet the entangled pairs last long enough to act as sensors, something that challenges our assumptions about how fragile quantum states must be. The bird's compass gives biologists reason to rethink boundaries that physicists thought were rigid. Plants reveal another quantum trick. Every green leaf engages in photosynthesis with an efficiency human-built solar panels can only envy. Capturing sunlight and delivering its energy to a reaction center looks simple on the surface, but for years it puzzled scientists. How does a plant funnel the energy from a fleeting photon to the right molecular site without wasting it as heat or scattering it away? Traditional physics had no satisfying explanation for such near-perfect efficiency. The answer appears to lie in coherence. When a photon is absorbed by a chlorophyll molecule, it excites an electron into a transferable packet of energy called an exciton. If excitons acted classically, they would stumble along a path, losing energy at each step. Instead, experiments suggest the exciton behaves as a quantum wave, spreading through the molecular network and exploring all possible routes at once. By settling on the fastest path, the exciton ensures energy reaches the reaction center with extraordinary speed. This quantum shortcut allows energy transport that borders on perfection. something almost no artificial system has been able to replicate. What makes this result more remarkable is its resilience inside a living cell. Vibrations, collisions, and constant molecular motion should destroy coherence almost instantly. Yet studies show agents maintain coherence for timescales long enough to complete their journey. Research at Lawrence Berkeley National Laboratory first observed these wave-like behaviors in 2010. Later studies in 2023 demonstrated that even a single photon can trigger this process, tracked step by step as it launched photosynthesis. That one photon was enough to power the reaction that begins the construction of sugars, emphasizes just how efficient the plant's machinery is. Human-designed electronics require precise isolation to display coherence. Plants achieve it effortlessly in air and sunlight. Taken together, robins navigating by entangled electrons and plants converting light through coherent excitons suggest that quantum mechanics is not confined to blackboards or particle accelerators. Instead, nature has been using it as part of life's operating system. Researchers even suspect similar mechanisms may be at play in enzymes where tunneling could help with otherwise improbable reactions or in proteins that transfer energy through coherence. Though these areas remain under study, the trend points to a broader theme. Quantum effects appear not as rare novelties, but as consistent tools that living organisms exploit. It is worth noting, though, that quantum biology remains an emerging field. The evidence is compelling and has been confirmed in carefully designed experiments, but the picture is incomplete. Scientists continue to debate how robust entanglement can be in living systems, how long coherence can last, and whether other processes share similar phenomena. The examples of robins and photosynthesis are well supported, but biology is complex, and establishing quantum principles across its full range will take time. What is clear is that the field is no longer fringe. It is active, respected, and fast evolving. The contrast could not be sharper. Laboratories spend millions to sustain entangled systems for fractions of a second. Meanwhile, a robin flits over a hedge, carrying quantum sensors in its eyes. Research teams inject huge resources into building more efficient solar technology. A leaf waves in the wind, conducting energy transfers with a quantum approach no engineer could yet match. Entanglement and coherence do not wait for us to build systems. They have been shaping life throughout its history. Consider the perspective this offers. A robin settling on a branch has unknowingly solved a problem that continues to challenge physicists: stable entanglement at body temperature. A leaf absorbs a photon and channels its energy nearly perfectly, outperforming billion-dollar solar farms at the scale of cells. These creatures and plants did not need theory to allow this. They simply embody it. The implication is humbling. What we view as extraordinary experiments are, in nature, routine acts of survival. Looking at the world this way changes the story we tell about entanglement. It is not a device humanity stumbled upon in the 20th century. It is a principle woven into life across millions of years. Birds fly guided by entangled electrons. Plants grow through quantum coherent excitons. If nature has relied on such effects without fanfare, perhaps it is no surprise to find that humans too might carry traces of similar processes in our own biology. And that realization points toward a mystery still more challenging. Because if elementary quantum phenomena can shape the eyes of birds and the leaves of plants, the question emerges, could equally strange effects be present in us? Specifically, might they appear in the processes that define how we think and experience the world? It is a possibility some researchers are testing now, asking whether the most puzzling of physical rules could underlie the most puzzling of human traits. Entanglement in human consciousness? Could one of the universe's strangest rules also touch one of our own deepest mysteries, the origin of conscious thought? That question now sits at the edge of scientific debate. For decades, researchers in neuroscience have described detailed maps of brain activity, showing how neurons fire and how circuits interact. Yet none of those scans explain why there is a subjective experience at all, why electrical signals and biochemistry should produce the sense of being an observer. Physicists, meanwhile, have wrestled with entanglement, in which particles remain connected in ways that seem to defy classical intuition. To some, it feels natural to ask whether these two unsolved puzzles might somehow connect. The cautious answer from most neuroscientists is no. The human brain operates in conditions thought to be hostile to quantum phenomena: wet, warm, and noisy. Quantum entanglement seems far too fragile to survive there. Under this view, thoughts are fully explainable as patterns emerging from billions of neurons exchanging electrochemical spikes. Scattered findings keep raising questions. Instead of confirming that consciousness can be neatly explained in classical terms, experiments sometimes reveal hints that quantum processes might contribute. Advocates propose that entanglement, normally seen only in delicate lab experiments, could persist in specific biological structures inside the brain. That possibility is not widely accepted, but it has moved from fringe speculation to a subject of cautious study. The most developed of these proposals is the orchestra theory, short for orchestrated objective reduction. Presented by physicist Roger Penrose and anesthesiologist Stuart Hameroff, it suggests that microtubules, tiny scaffolding elements inside neurons, are not just supports for the cell, but hosts for quantum states. According to the theory, these states sometimes collapse in ways linked to moments of conscious experience, creating brief protoconscious events that combine into a continuous flow. Crucially, the theory does not assert that microtubules unquestionably generate consciousness. Instead, it claims they could be sites where quantum processes interact with neural activity. This difference matters. Mainstream neuroscience regards orchestro as a provocative but highly speculative model, while many scientists remain skeptical it can work under biological conditions. In labs, entanglement requires extreme isolation, cooling to near absolute zero, shielding from interference, or carefully engineered materials. Inside a neuron, quantum states will be constantly disturbed by heat and molecular motion. For orchestra, or to be viable, microtubules must not only support coherent quantum activity but protect it long enough to influence neural operations. Critics argue this is implausible. Supporters, however, note that coherence has been observed in unexpected environments, such as plant molecules and bird retinas, suggesting that biology may have evolved ways to stabilize such states. Whether neurons share this ability remains an open question. Intriguing pieces of evidence have emerged from anesthesiology. Anesthetics are notoriously simple molecules, yet they can shut down consciousness quickly and reliably. How such tiny compounds exert such sweeping effects has long been unclear. A 2018 study added a curious twist: different isotopes of xenon gas, identical in chemistry but distinct in nuclear spin, a quantum property, produced different anesthetic outcomes in mice. If brain activity were purely classical, these spin differences should not matter. The fact that they did suggests that quantum parameters may influence whether consciousness fades or persists. Although far from definitive, the result aligned with the idea that quantum details matter where awareness is concerned. Further support came from a 2024 study at Wellesley College. Researchers gave rats a drug known to bind specifically to microtubules, then exposed them to anesthetic gases. Strikingly, animals treated with the drug took longer to lose consciousness compared to untreated controls. The team concluded that anesthetics may impair awareness by disrupting microtubule activity, consistent with the idea that these structures are important for maintaining consciousness. While the findings do not prove orchestra-OR's mechanisms, they provide a measurable link between microtubules, anesthesia, and awareness that classical circuitry alone struggles to explain. The medical implications are considerable. If quantum properties of microtubules are genuinely relevant, then interventions might one day target them to alter aspects of consciousness. This could lend new insight into why disorders like Alzheimer's or schizophrenia distort perception, or why some patients in comas show signs of awareness while others do not. Traditional neuroscience focuses on electrical signals and neurotransmitters. A quantum framework might highlight overlooked processes governing how awareness switches on and off. The lesson here is not that consciousness has been explained, but that alternative perspectives could enrich our understanding of illnesses deeply tied to the mind. Still, most neuroscientists remain unconvinced. They argue that classical models account for much of what we observe, and that speculation about quantum states risks distracting from proven mechanisms. Until evidence shows entanglement persisting reliably within neurons, any link to consciousness must be considered tentative. Researchers like Christoph Koch acknowledge the importance of exploring these ideas, but emphasize that existing findings are preliminary and open to multiple interpretations. Even supporters of orchestral are concede that much more work is required before it can approach mainstream acceptance. For now, it is a provocative hypothesis rather than a settled explanation. That balance between intrigue and skepticism is crucial. On one hand, if entanglement truly operates within the brain, it could reshape how we think about awareness, casting it not as an emergent trick of meeting chemistry, but as something tied to the same physical laws binding particles. It might even suggest that consciousness is more deeply connected to the universe's fabric than assumed. On the other hand, it remains a huge if. Evidence so far is suggestive, not conclusive, and the possibility must be treated as an open question rather than fact. This tension fuels continuing experiments. Researchers probe microtubules, anesthetics, and neural responses, seeking signals that either support or rule out the quantum case. For viewers outside science, the appeal of this idea is clear. It promises to link the mystery of human experience to the strangeness of quantum mechanics. Advocates imagine bold implications, that consciousness might not be unique to humans, that it could reflect universal processes, or that measuring quantum coherence in brains might someday help determine if a patient is aware. Critics answer that these possibilities remain speculative and risk overstating limited results. Both sides agree on one point: the question of what consciousness is remains unanswered. This is a curiosity gap that makes the topic hard to ignore. If consciousness one day proves connected to entanglement, our view of human nature and our place in the cosmos would change dramatically. Diagnosing coma patients, understanding how drugs alter awareness, even exploring whether simple organisms experience rudimentary perception. All of these questions would be reframed. But for now, the evidence represents possibility, not proof. Consciousness sits at this contested frontier, fascinating and unsettled. Experiments continue to test whether entangled states may help explain its workings, but the jury is far from delivering a final verdict. What is certain is that entanglement inspires speculation alongside rigorous science, pulling attention not only because it may explain mysteries of the mind, but also because of the misconceptions it regularly sparks. And that brings us to a different problem: how entanglement is often misunderstood entirely. Common misconceptions about entanglement. For many, the mere mention of entanglement conjures images shaped by science fiction. It is easy to picture distant particles whispering signals across galaxies, people vanishing into light beams, or secret channels that disobey time itself. Popular culture has cemented those images, and news headlines often magnify them. But this is exactly where confusion begins. The real physics is stranger than fiction, but not in the way people imagine. Entanglement does not grant faster-than-light chats or teleporting spacecraft. To get an accurate picture, the myths need to be separated from what experiments have actually confirmed. The first and most stubborn misconception is the idea of entanglement as a faster-than-light messaging service. The reasoning sounds simple. Two entangled particles remain linked no matter the separation. Measure one and the other reflects a matching property instantly. Shouldn't this allow instant signaling, outpacing light itself? The answer is a decisive no, and the reason is the key detail many explanations miss. The outcomes of measurements are completely random. You cannot choose whether your particle registers as up or down, 0, 1. Because the outcome is uncontrollable, you cannot encode a message into it. The correlation only becomes visible later when you compare results over a classical communication channel, one still bounded by light speed. Entanglement produces striking patterns but not steering power. No control means no signal. This point has been tested directly. In 2015, physicists carried out so-called loophole-free Bell tests, closing off all gaps critics once argued might explain the effect away. Correlated results appeared instantly across large distances, but the no signaling rule remained intact. Observed outcomes were random locally, and nothing could be sent faster than light. The experiments did not weaken entanglement, they proved it, but they also showed why it will never function as an instant telephone line across the cosmos. A related myth concerns teleportation. Quantum teleportation is a rigorously tested protocol, but what travels is not an object, or even a particle. It is a quantum state. The particle holding the state at one location is measured in a way that destroys that information, while its twin, entangled with a partner particle elsewhere, recreates the state exactly. For the reconstruction to succeed, a few classical signals must still be shared, and those move no faster than the speed of light. The result is faithful state transfer, with no object crossing the middle. That is practical and precise, but it is not a transporter moving ships or people. The word teleportation invites confusion, yet its meaning in physics is narrower. States, not matter, move information, not mass. A third misconception emerges naturally from mixing the first two, that entanglement permits time-defying signals. If correlations appear instantly, perhaps they can be set up to send information backward, beating cause and effect. Here again, the issue is randomness. No one can control measurement outcomes in advance, which makes encoding messages impossible. No adjustable channel exists to send instructions into the past. Experiments that stretch entanglement links across kilometers, mountain ranges, and even satellites orbiting Earth all produce the same result. Correlations arise with no delay, but no usable information leaps over time's order. Relativity's structure remains untouched. Why do these misinterpretations persist? Often, the language in public reports nudges readers toward them. When a landmark experiment verifies entanglement at new scales, headlines sometimes frame it as instant communication or superluminal signaling. The raw data never implies those abilities, but the phrasing sticks. To a casual audience, a story about breaking light speed sounds irresistible, while the subtler truth that randomness enforces limits sounds unsatisfying. Yet the subtler truth is the fascinating one. Entanglement is real. Correlations are instantaneous, and still no information can be sent any faster than before. Clarifying these myths is not meant to diminish entanglement's importance. If anything, the fact that correlations arrive with zero time delay while still obeying no signaling rules makes the phenomenon more remarkable, not less. It highlights why Einstein found entanglement so unsettling. Decades of Bell test refinements have ruled out hidden variables. Two particles separated by any distance retain the marks of a shared state as though they are one system stretched over space. That oneness, seen only in the statistics revealed afterward, challenges any classical description of reality. The absence of faster-than-light messages does not weaken entanglement. It defines its strange boundary between what is connected and what is communicable. And rather than leaving us empty-handed, that strange boundary is exactly what allows practical uses. Because measurement outcomes are uncontrollable, hackers cannot hijack an entanglement channel to copy information invisibly. Because state transfer requires a classical signal, teleportation is secure rather than leaky. Quantum key distribution, teleportation protocols, and entanglement-based computing all exploit the fact that entanglement cannot be faked or intercepted without leaving visible errors. The very reasons entanglement cannot send instant phone calls across galaxies are also the reasons it can underpin unbreakable encryption and reliable quantum processors. Stripped of myths, the real phenomenon remains extraordinary. A photon in one laboratory behaves as part of a unified pattern with a partner photon far away. Networks use those links to guarantee secrecy. Parents of tomorrow's encryption systems rest on fragile correlations tested and retested in physics labs. Quantum teleportation spreads not people, but information across fiber networks and satellites. Every step is constrained by relativity, yet every step builds tools that were once impossible. It may seem disappointing if one hoped for spacecraft teleporters or violation of light speed limit. But the reality turns out stranger and, in practical terms, more useful. Entanglement is neither magic nor science fiction. It is a rule written into the world's structure, sharp, testable, and reproducible. That is what makes it powerful. Not magic, but a new rule book, stranger and safer than sci-fi. And it is this rule book, once speculative, that now guides a moment we are living through. The years when the spooky is leaving physics textbooks and taking shape in real systems. The next natural question, then, is why now? Why this moment? Marks the turning point from puzzle to tool. Why 2025 is the year of spooky technology. In 2025, entanglement is no longer treated as a curiosity tucked away in physics journals. It now anchors pilot networks, early-stage processors, and experimental satellites, making this year stand out as a tipping point. Nearly a century after Einstein's dismissal, the phenomenon has moved through decades of validation and refinement, and today its effects are arriving as part of functioning testbeds that connect cities, laboratories, and even orbit. The shift is not about a finished product. There is no completed global quantum internet waiting to be switched on, but about the moment these separate advances align into visible infrastructure. The clearest place to see this is in communication. Across continents, governments and industries are weaving quantum key distribution into live systems. These efforts are motivated not by the promise of higher bandwidth for streaming or new gadgets, but by security. Most encryption currently in use relies on mathematical puzzles. Quantum computers, once they scale, will break those puzzles with relative ease. The urgency of 2025 comes from the recognition that defenders cannot wait for that break before moving to alternatives. Entanglement delivers such an alternative by ensuring that interception leaves a permanent scar in the communication channel. Those scars are not theoretical, they show up directly in the data. Europe's EuroQCI initiative demonstrates this shift most clearly. The project is not stationary reports or discussion papers anymore. It is transforming existing telecom infrastructure into secure quantum channels. Fibers that once carried only internet traffic now host entangled photon pairs transmitted between major institutions. European Space Agency efforts add satellite connections to extend these links overhead, ensuring that whole regions benefit rather than individual cities. The lesson is not just that quantum-secure communication is possible, but that it coexists with classical traffic already pulsing through the same infrastructure. Health systems, financial records, and government communications can layer their security on firm physical foundations. China, having invested in large-scale efforts years earlier, began with its Prometheus satellite, launched in 2016, which sent entangled photons across stretches of over 1,200 kilometers. By 2025, lessons from that program are active in a continental-scale network of ground stations, banks, and research institutions. More satellites are planned before 2027 to broaden coverage, but the key fact is present-day functionality. Large cities already use these protected routes, whether or not citizens realize it. When funds or messages move across China's secure channels, entanglement makes tampering visible and interception impossible. In North America, the emphasis is on close collaboration between public research and private firms. National laboratories and technology companies run pilot systems in Chicago, Los Alamos, and several coastal hubs, connecting banks, defense agencies, and universities. These are not promotional showcases. They carry real trial traffic and protect contracts and datasets where mistakes would be costly. The American approach highlights the competitive but converging character of 2025. Regional projects differ, but their goals point toward the same emergent structure, a functional prelude to a quantum internet. Teleportation is another development stepping out of theory. For many years, experiments managed single photons over short distances. Those distances grew, first within laboratories, then across campuses, and later between satellites and Earth. In 2024, teams at Kyoto and Hiroshima universities achieved measurements of the W state, a complex arrangement where entanglement binds more than two particles. This expands the possibilities beyond simple one-to-one teleportation, allowing multiple nodes to share interconnected resources. For early network designs, this capacity matters because it makes routing and distribution more flexible. Another example came in 2025 with a chip-to-chip teleportation experiment over 12.3 kilometers of optical fiber. Silicon photonic processors exchange quantum states not as abstract entities, but as functioning nodes on a line, echoing what a scaled network of the future might require. Far from being a concept alone, teleportation now stabilizes fragile signals from one segment to the next, a technique essential for quantum repeaters. Research from Innsbruck has shown entanglement swapping, chaining nodes by teleporting states across them, can extend range far beyond the losses of ordinary fiber. With these improvements, the spine of long-distance quantum communication systems takes shape. Computation is the third area where 2025 represents more than incremental steps. Early quantum computers with tens of qubits often produce noisy, unstable calculations. To move further, scalability had to be solved. Instead of building one giant machine prone to collapse, Oxford researchers demonstrated a networked approach, linking two independent processors through an entangled photonic interface so they acted as one. This architecture is a demonstration of distributed quantum computing, pointing towards systems that could connect many nodes. The scalability bottleneck, while not solved, now has a working prototype for bypassing it. For practical industries, these increments are not abstractions. Pharmaceutical developers are exploring quantum simulations for protein folding and drug discovery, where classical models collapse under complexity. Material scientists turn to entanglement-based processors for designing catalysts and investigating superconductive compounds. Logistics firms adopt pilot optimization routines, aiming to streamline routes and reduce costs in networks extending across continents. Each of these tasks aligns with computation that explodes in complexity when approached by ordinary supercomputers. Entanglement collapses that complexity by representing multiple possibilities at once and steering interference toward consistent results. When these fronts, communication, teleportation, computation, are viewed together, the sense of timing in 2025 becomes clearer. Entanglement has been experimentally validated for decades, but its applications remain confined to controlled demonstrations. In the span of the past few years, those demonstrations have shifted to infrastructure, satellites bridging continents, fibers embedded in cities, pilot processors solving once intractable calculations. The year's significance comes not from a single discovery, but from convergence. Different paths of research have matured at once, creating interconnected testbeds that function as early operational platforms. This convergence explains why 2025 looks like a pivot point rather than one milestone among many. If it were only one satellite, the importance would be limited. If it were only one lab connecting two processors, the signal would be interesting but isolated. Instead, multiple regions, industries, and scholarly groups have crossed similar thresholds together. The result is momentum. Communication links expand alongside chip-to-chip experiments, repeaters extend range while distributed processors prove scalable systems are workable. Together, they mark the moment entanglement stopped being defined solely as experimental fact and began being recognized as technological infrastructure. What would Einstein make of this transformation? He might still raise an eyebrow at bold promises, but the symbolism is hard to miss. A phenomenon he once mocked now underwrites secure routes between governments and banks. A phrase he intended as suspicion, spooky action, has been borrowed to name the very networks being built today. Some researchers even joke about spookiness as shorthand for this unfolding quantum infrastructure. The irony of Einstein's phrase in surviving when his objection has not provides a useful reminder. Skepticism sparks progress, and sometimes the features that seem most absurd are the ones that grow into foundations. Yet what really matters is not the irony, but the implications. The world is watching an abstract rule of subatomic behavior transform into the hidden machinery of communication and computation. This change will not arrive as a sudden revolution with glowing hardware in every house. It filters in quietly instead, in the exchanges of banks, in the pathways of satellites, in universities running distributed processors. Beneath the surface lies a fundamental realignment. An idea once dismissed is now installed as the spine of infrastructure. The significance of 2025 lies not in spectacle, but in the way these quiet changes accumulate. Entanglement, mocked as unworkable and doubted as fragile, now provides the trust behind high-value communication. It carries information faithfully across networks and powers calculations that classical processors cannot reach. The story has been defined in less than a century by doubt, confirmation, and finally integration. That history makes its presence in 2025 remarkable because entanglement can no longer be treated as distant or speculative. And while experts acknowledge these achievements, a fair question remains. If most of these systems work invisibly, why should they matter to anyone beyond researchers and policymakers? To answer that requires stepping away from satellites and processors for a moment and looking closer at everyday life, where trust, privacy, and our sense of connection all come into play. The bigger picture. What spooky action means for us. Why should phenomena between particles smaller than dust grains matter to ordinary people at all? At first glance, entanglement seems too abstract. Photons linking across space while you shop, work, or stream a film feels irrelevant. Yet in 2025, entanglement has shifted from obscure physics to forming part of the invisible scaffolding of society. It now supports how banks transfer funds, how hospitals protect patient information, and how governments conduct secure communication. What is changing is not only the scope of technology, but the deeper idea of trust itself. For centuries, trust in information required layers of defense. Wax seals closed letters. Later, ciphers cloaked telegrams. The digital era introduced encryption, built on mathematical puzzles, resistant but never permanent. Every code carried an expiration date, depending on the strength of machines trying to break it. That uneasy balance left privacy in a constant race. Firewalls patched after attacks, monitoring systems chasing intruders after entry. Entanglement alters this landscape. Security no longer rests on probability, but on rules woven into nature. Quantum key distribution, QKD, applies this principle. Two participants share photons prepared in entangled states. Each makes random measurements. If their correlations remain intact, the shared key is safe. If a third party attempts interference, the disturbance shows up instantly in the statistics. No guesswork is required. The interference is revealed immediately. Already, governments and industries unable to afford even minor breaches, banks, defense agencies, healthcare organizations are piloting QKD in controlled networks. Canada's National Quantum Strategy explicitly prioritizes this transition, pairing QKD with post-quantum cryptography to prepare for future risks. These are not hypothetical interests. They are on-the-ground roadmaps guiding real infrastructure. The idea may sound abstract, but it filters into daily digital habits. Each login assumes secrecy. Each medical record stored assumes protection. These routines depend on hidden layers of security, usually invisible until something fails. With quantum systems, a compromised channel does not remain silent. It exposes itself. Privacy is not absolute, but the ability to hide intrusion is made far harder, even impossible, without leaving detectable traces. That shift converts what felt like fragile hope into a more stable expectation. It reaches anyone who relies on the digital trails of identity, finance, and memory. And the impact of entanglement extends far beyond security. In computing, qubits linked by entanglement solve tasks beyond silicon's reach. Protein folding, molecular design, and global logistics networks fall into complexity too vast for linear machines. Entanglement allows these problems to be restructured, enabling solutions in fields that affect daily life. Pharmaceutical firms see shorter development cycles for drugs. Biotechnology companies identify molecular interactions with new accuracy, and shipping networks optimize traffic to save resources. While invisible at the surface, these subtle ripples shaped by entanglement affect how quickly treatments reach patients, how efficiently goods circulate, and how economic costs are managed. The social dimension of trust is just as important. With conventional digital systems, stories of leaks, stolen identities, or compromised elections have dominated for decades. The default assumption became one of vulnerability. Quantum secure channels shift this expectation. As pilot deployments grow, communication where interception can no longer go undetected nurtures a different cultural posture, confidence over suspicion. People begin to assume defense instead of inevitable breach. That change alters not only infrastructure, but the emotional environment of digital life. Entanglement also reframes how we imagine connection itself. In physics, it shows particles remain one system despite distance. In networks, it means that information shared within quantum channels has assurance without needing layers of external trust. Metaphorically, societies also operate like separate entities linked by bonds that keep them coherent. Seeing entanglement built into working tools provides a tangible illustration of connection where distance need not mean doubt, and honesty is guaranteed by the medium instead of fragile agreements. This model differs sharply from earlier technologies. Printing copied words across pages. Telephones transmitted voices. Radio carried broadcasts through the air. Computers exchanged numbers as electrical currents. Each expanded reach but still risked interference, distortion, or silent copying. Entanglement alters the medium. Any attempt to copy breaks the state. Honesty is not promised by users but embedded in the channel itself. This is why experts describe the present moment as more than incremental, advance. It is a redrawing of how information is understood, less about passive defense and more about active verification as part of transmission. The emerging quantum internet exemplifies this coexistence. It will not displace the internet people already rely on for videos, emails, and trade. Instead, it forms a parallel structure. Classical systems offer speed and convenience, while quantum networks handle the most sensitive exchanges. Your next movie streams over classical pipelines, while quantum links carry financial transfers or government discussions. Hybrid services integrate both, invisible to most users but crucial for maintaining trust. This phased coexistence avoids abrupt replacement and aligns with national strategies worldwide, ensuring integration is measured, not rushed. Looking ahead, hybridization will deepen. Nodes will translate between classical and quantum protocols, assigning workloads where they fit best. Distributed quantum cloud systems will emerge, linking many limited processors into larger virtual machines. Algorithms for quantum-enhanced AI may handle tasks ill-suited to classical designs. These applications may seem remote, but impact everyday life indirectly. Authentication systems that prove identity without divulging personal data, or scientific collaborations moving secure data across oceans. Users may not notice entanglement at work, but they will feel its results in efficiency, privacy, and reliability. Importantly, none of this breaks the boundaries of physics. Teleportation, as used in testbeds, still requires classical channels moving at light speed. Entanglement connections may appear instantaneous, but no message travels faster than relativity permits. What they deliver instead is certainty. Certainty that interception causes disturbance. Certainty that secrets remain undisclosed. Certainty that solutions emerge in systems too complex for classical computation alone. Certainty, not spectacle, becomes the defining feature of this transition. So why should tiny quantum effects matter to anyone outside laboratories? Because they are recalibrating the foundations of modern life. Trust in financial systems, trust in hospitals, trust in communication across borders. All of these depend on secure, reliable flow of information. Add to that the ability to analyze complex biological and industrial problems at new scales, and the outcomes ripple through every domain of society. These advances arrive gradually in pilot deployments and hybrid networks, but they touch the most essential systems people rely on daily. Einstein once doubted whether entanglement could be real, yet today the world is beginning to construct its social infrastructure upon it. The broader picture is less about physics alone and more about how humans relate, share, and protect what matters. From this point on, information itself is becoming entwined with entangled bonds, and it raises a question that lingers as societies adopt these strange tools into ordinary life. What will privacy feel like when it is guaranteed not by code, but by physics? Einstein once dismissed entanglement as an illusion, a footnote destined to vanish under better theories. Yet in 2025, that same spooky action has become central to real systems. It underpins secure communication through quantum key distribution, drives quantum computers that solve problems beyond classical reach, and even appears in biology, from bird navigation to photosynthesis. What began as a puzzle now shapes critical sectors that guide economies, medicine, and technology. So the question circles back to you. How do you imagine life in a world where trust and connection rest on quantum rules? If you found this mind-bending, hit subscribe for more explorations in the science that is quietly reshaping how we live.